Let's see what that does.
I hope you can see my thing.
Oh, there we go.
Okay, we can see your slides.
Okay.
Perfect.
So first, let me just discuss why I chose this paper. So maybe you all know that I'm working on exoplanets. So I got interested in exoplanets because I had a previous background with scientific Olympiads, especially Earth Science and Astronomy Olympiad. So my key interest in astronomy was because of back in 2010 I watched Avatar the movie, and I got very interested in the geology of exoplanets. So I basically chose this project for this year. So I chose this paper because when I was starting to understand what I'm doing, what I'm going to do was I was going to look at the carbon to oxygen ratio of hot Jupiter. But because of the pandemic and other things, we couldn't get the data that we're supposed to get from Hawaii, I guess, that my advisor Aurora said. So now we are working on a different project that is finding titanium oxide and vanadium oxide from the same hot Jupiter we're supposed to look at for carbon to oxygen ratio. So basically what I started doing just after getting to know what my project was, because I had a sudden change of my project. So I started to look up at the papers that are relevant to my project. That's the usual case what we will do. So I found this particular paper back in May that I started to read. It gives just a simple overview how the exoplanetary atmosphere works and how to detect exoplanetary atmosphere. But still then I didn't know the actual process that I'm currently know that, because I'm working on that particular thing. But this paper gives a total overview. So if you want to check out the paper, you can see the active link here. So we are talking about exoplanet and atmosphere. So first I'm giving two news. First, Eid Mubarak, because tomorrow is the second Eid of the year for Muslims all over the world, and it is supposed to be 31st July for you guys and 1st August for me. And the second news is that I have opened a journal club in my country. That is the second ever journal club for all the students here in Bangladesh who are interested in astronomy. So that's the thing. Next, we get straight into the paper. Okay.
Great.
So if you think what is BDOA, BDOA is the Bangladesh Olympiad and Astronomy Institute. Okay.
Fahim, will you be able to meet in person or will it be over online?
Currently, we are planning to do it online as we are doing now. And I think doing it online has more advantages because you can share the slide and you don't have to go in a certain place. But in later time or maybe next year, we can start doing some workshops manually or in physical presence. But for now, I'm going to do it online. And you all guys are invited if you want to just present paper in our journal club. So
Great.
that's the thing.
Thank you.
Okay. So straight to the paper. Why I'm, as I said, that why I'm using or chose this paper particularly. So this paper, as you see, that it summarizes all the process that exoplanetary atmospheric scientists should know. It basically tell us what steps to follow and how to just look for atmospheres and what are the process involved. So that's why This is the okay. So the main thing is we are looking into the exoplanets and the so I would like to draw some things. So main thing we are looking at the exoplanets, right? So what do you think? Which exoplanets would be the best to observe uh, from Earth? Any suggestions? Rocky planets, um, Jupiter-sized planets. What would be the uh, most favorable planet to look for? Any suggestions?
I guess it depends on the method, but here we're talking about the transit method.
Yes.
Okay.
So
Stars that are close to the sun. I mean, planets that are close to their star or massive one.
so we have a special term that describes exactly what the thing we want to get. That we want to get a planet that is large enough that we can we can basically see the transit depth, which is this thing, and we want to also find the planet atmosphere large enough that we can measure some atmosphere, because so what planet basically uh, explains the both situation is hot Jupiters, because you can see the hot Jupiters are large enough and close enough, because uh, suppose this is a planet, if it is large enough you can see the transit depth, and if it is close enough to the planet you can see that the planet is actually transiting or not. So hot Jupiters are very specific and fancy thing in explanatory sciences, and the most paper I read past 3 or 4 months are related to somehow related to hot Jupiters, because my work also is related to hot Jupiters. I am looking to at the hot Jupiter at 76 B. So hot Jupiters are important, and you can guess why it's important. And this paper basically gives an idea of how hot Jupiters can be found using transit methods, and hot Jupiters are very favorable for transit methods. So, okay, now let's talk about why transits are cool. Uh, Transits are cool because if you want to see transit, you have to have like uh, the inclination of the orbit must be close to 90 degrees, or we can say that we can thank you for this edge on. So if it's close to 90 degrees, we can basically see the transit, and if it gets close to zero, and it won't be a transit. It may look like something like this. So if you're looking from this angle, it's rarely transit because it misses the whole uh, line of sight. Okay. I don't think my drawing is that particularly like exact, but I think you get the gist. So another thing is when we are looking at the hot Jupiters or some planets like that, we can expect it to be tidally locked. And what tidally locked planets do is their orbits get close to the circular orbit, so it is easier for us to measure the radial velocity. If the inclination and the eccentricity of the orbit gets bizarre, maybe a few weeks ago, my advisor Aurora presented a paper which basically described that if what we can expect from eccentricity and how to like differentiate between brown dwarfs and hot Jupiters and large Jupiter-sized planets. So eccentricity is very important thing. But for hot Jupiter, we get that this particular planet have very close to circular orbit. So that's a plus point for us. Um, so these 2 points are particularly mentioned in this paper. So I just thought that it would be cool to mention here in this sense. So as you can see that it's a graph from the paper, and you can see that for uh, the first diagram just shows us how to remove. The first diagram just shows us the transit of hot Jupiter, and maybe it's from what 12B or something like that, and they are looking into the um, infrared and optical regions of the sky. So you can see that there is a significant depth in the transit curve, and here if you can see that the transit like 0.997, so it's significant for us. You may think if you are not into exoplanets and maybe eclipsing binary stars, you may think this is very less for a transit depth, but for exoplanetary scientists or eclipsing or who studies eclipsing binary stars, it's very like important for us to get enough transit depth. And for hot Jupiter, it's significant. So if you want to know fun fact that the Tabby star, uh, the basically the discoverer of the star is the astronomer. The name of the astronomer was Tabby. She presented a TED talk. So she found a star that is unusual amount of depth, and it's not supposed to be a hot Jupiter. So it is a matter of debate that what kind of star or what kind of object can produce so much depth in the transit, and people are like coming up with a theories that it may be a Dyson sphere or any alien structure. So it is a interesting paper if you want to read. The paper title is "Where is the Flux?" So you can search it in Google, like what the flux WTF paper of Tabstar. It is a very popular thing. So let's move on to the second. So this paper tells us basically these things. So I'm going to just show you what the paper actually shows us. So first, the paper tells us what wavelength should we observe. So it is preferable that if you are using massive Neptune-sized planet or some planets are that very massive but not massive enough to be a Jupiter or Neptune-sized planet, we should observe the planet using optical or infrared spectrum. And why this is the case? Because the signal to noise ratio, as it says just here, the signal to noise ratio increases if you use the visible and infrared spectrum. So I won't be getting too deep in the paper. So I'm just going to scroll through and just mention the basic facts. So another thing you want to get is want to know about the secondary eclipse. So again, maybe I have to draw a diagram so that I can show you what is the secondary eclipse. So suppose this is our star and this is the orbit of the planet and this is the planet. So if we see the transit curve for this particular position, it may look like this. And again, so this is our transit, okay? But if this planet, like, if this planet goes behind the star, this is somewhat called the eclipse of the planet, or the, so this is the secondary eclipse. So this part of the paper basically mentions why secondary eclipse is important for us. So again, you can see the diagram I just showed about the hot Jupiter, and it also mentions a few equations and methods of uh, measuring the transit depth using photometric bandpass, as you can see. So next we'll move on to phase curves. So phase curves are the thing that if the planet is just uh, above the or in your line of sight of like planet or the star, the phase is take to be 0, and the planet, if the secondary eclipse happens, it take to be 1 maybe. So why phase is important? Because calculating the phase, you can basically say how in a given period of time how much the planet has eclipsed or transited the star. So it is important because when you are using time series analysis, it is important to know how many times the planet revolves the star. So, and then you can use the data to organize the transits according to time, and then you can measure the flux and other properties like radial velocity and other things in organized manner. So phase is important. So again, the third thing is the next thing is the transit, and why the transit is important I already have mentioned to you. So this part of the paper basically explains the geometry or algebraic expression of the transit. Okay, there is some cool uh, diagram here. So eclipse mapping is another thing that when the star eclipses the planet, but it may not eclipse the whole thing because of the, again, the inclination of the orbit, eccentricity of the orbit. It may just uh, hide a portion of the planet or limb of a planet. Then we can measure the atmosphere of the planet in that exact moment, because when this kind of thing happens, like here is a, this kind of thing happen. So as you can see, again I'm going another thing. So when we are seeing the light, and you can see the light will move to, suppose this is the scale height of the atmosphere. When the star light passes through this portion of the atmosphere, we'll get some transmission spectra. So eclipse mapping is another important thing that we look for. So, and now move on to the next part.
Right, what is the red dot?
Red dot. This music, right?
Yeah.
Let me see. I haven't said that. Let us find out together.
Okay, I guess it could be the non-uniform bright disk. The hot region. If the planet has a hot region, I guess, then it will look a bit different in the transmission, I think is.
Maybe something like that. Aura, if aura was here, it would be better for us to understand this thing. But at the moment, I don't know what is the exact thing at the great point of the planet like shows us. So I'll be skipping that, but maybe in the chats or something I will get the answer from Aura or Alex, then I can tell you guys about it. Okay, so here is the full geometry about how the flux is covered. As you can see, if this, so if the planet, the star obscures this part of the like ring, or you can say stripe, the flux depth will be measured from this portion of the depth, and again for this you can see. So the geometry is cool, but wouldn't be easy to describe to like total total newbies who don't know about the transit geometry on how transit works. So I'll be skipping this again. So here is the important thing. Again, I'm going back to the slide. So when you are doing explanatory sciences, what method do you prefer? So is there anyone who is working on photometry? I don't know. Is there anyone who is working on photometry of anything like stars or clusters or something?
I'm not, sorry. Just doing spectroscopy.
I'm also doing spectroscopy. So my question to you, what method do you prefer, or this far, or which method do you prefer to do this kind of explanatory sciences? Any guess? Photometry or spectroscopy? Which method do you want to do in like atmospheric science or
I guess,
explanatory science?
I mean, you need to do both. I guess you want to do the photometry to detect the planet, and then spectroscopy to characterize the planet.
But we're talking about like atmospheric sciences of the exoplanets.
Okay.
So which method do you prefer?
Spectroscopy.
Yeah.
Okay. So this paper also mentions why this is the case. Which method we should prefer? Because the paper basically mentions that photometry is useful, and we can do lots of things using photometry. As the paper says that photometry collects radiation using broad wavelength ranges. Okay, but at disadvantage of spectroscopy is that it narrows down the wavelength region of the signal. So which method do we want to do the atmospheric science? So both in case of photometry and spectroscopy, there is a thing that spectral resolution, and in photometry the spectral resolution is very low, as this paper mentions. So, and for atmospheric science or detection of atmospheric species, we need high resolution data. So of course high resolving power is always desirable. So spectroscopy basically gives us the high resolution data of any atmosphere. So spectroscopy is always preferable for us. And it also mentions why this is the case. But for this particular paper, if this paper shows us any kind of data that shows which method is widely used among astronomers, it would be helpful for any people starting at explanatory sciences. So I found this portion of the paper lacking in this case, because when you have two methods of doing a certain thing, if there is a data available, you can choose like for a total new person who is totally new to this kind of thing. It would be helpful for anyone to just see the data and see what others are doing, like what other scientists or astronomers are preparing to do their job for atmosphere of exoplanet. So I found lacking this portion of the thing. hope that if some kind of paper shows any data that whose method is more preferable or has very less uncertainties, this paper would be like a total package. So there is the case that this paper doesn't have any kind of data for that, but it explains why the case. And again, this paper also mentions that spectroscopy or exoplanet is easy to interpret uh, because signal to noise, adequate amount of signal to noise is found because of spectroscopy. And who maybe we are working with I'm also working with high resolution spectroscopic data, so I can see the signal to noise ratio is like very adequate amount of signal to noise ratio. So we found that it's very easy to reduce our scalar or start date data and figure it out or fetch out the exact data we want. That when we are talking or working with start data or exoplanet data, there is a two kind of data. So we'll get both start data and exoplanet data. But as the start data is always much bigger, we have to remove the start data and then using correlation method, which I'm just getting hang of. The cross correlation method is just a method that increase the probability of detecting a certain species, a certain amount of function data that you have. Basically, you have a model and you will be matching the model with your data. So when your predicted model peak and your data peak matches, and it will increase the peak and something like that. Maybe Sarah can better explain the cross correlation method to us, or maybe you guys can. So, cross correlation method and spectroscopy is very important for atmospheric sciences for exoplanet. What the exact thing I'm doing currently now? I'm currently doing the cross correlation thing. So the next thing is which telescope is preferable? Of course, because we are looking at a certain thing like exoplanets and their atmosphere, it is easy to say that we will be preferring space-based telescopes like Hubble, Spitzer, and other things. So, but nowadays, this paper also mentions that nowadays we have certain amount of large telescopes and spectroscopes that we can measure high resolution data from ground. And I'm also using high resolution data from ground from Permanence Color Alto Observatory, Permanence spectroscope or something like that. So this paper also mentions that specific thing uh, which ground or space telescope is important for us. Okay. So let's move on to now this paper mentions how to interpret measurements. So I'm not going in depth to this portion. I'm also skipping this portion of the paper because it will be hard to explain in a short amount of time. So here is another cool diagram which shows the after cross-correlating and getting the species matched, which kind of uh, species you would like to or you will be likely to get. But here this paper shows water, methane, carbon monoxide, carbon dioxide, but it would be it would be helpful for me basically if it had titanium oxide or vanadium oxide data, but it doesn't have that. So here are some cool statistical measurement of exoplanets or something. Again, I'm taking that extrasolar activity. Of course, there will be stellar activity. Okay, so we have already talked about groundwork. Now the important thing is the future. So we came to the conclusion that space-based telescope is obviously important for us, and it will provide us more data, more high-resolution data. And scientists or astronomers all over the world is expecting the James Webb Telescope to launch and get more fancy data, but we are getting this mean basically explains our feelings that it's getting delayed and delayed and delayed, and we're not. I don't think I would see James Webb Telescope launching in my lifetime, because during this current pandemic situation, and I'm already suffered from coronavirus, but I survived. But I don't know if I'm going to like observe James Webb Telescope launching from Earth. Maybe, don't know. So here is the conclusion that the paper also mentions what James Webb Telescope and other space telescopes will likely to provide us in the future, and it gives us a predicted model how the uh, data can be observed using several uh, several data. So there is something like again some time series analysis from predicted model of shock and ELTs. So and there is some molecular of oxygen. Okay. This particular diagram is for atmosphere of Earth. How we can use our solar system to predict and observe extrasolar systems in our universe. Okay, so this is the end of my presentation. Any suggestions for me or to improve my presentation, or any questions you maybe you have? Because I'm done with my presentation, I guess. It is like my second presentation ever for a scientific paper, but I'm still getting the hang of it. I don't know how you will like it or not, but I tried.
Yeah, no, I think you did a good job combining the two different styles of presentation as well, with the slides and the going through the paper, and your drawings were good. And it's also hard to, because this is like a review introductory paper, so it is hard to talk about everything in such a short amount of time. I guess, yeah, people, do we have questions? I have some. I have a question. You said in your work that you're doing with Aurora, you're looking at titanium oxide, or?
Yes, titanium oxide and vanadium oxide, because it is a fancy thing that titanium oxide, just like in our oceans, there is certain heat inversion. Like in our ocean, there is a thing that when heated stream flows and suddenly somehow for some special reasons and occasions, the inversion happens in our oceans, like hot water inverses and goes up and cool water goes down. So titanium oxide also does the same thing for exoplanets, because it can somehow inverse the atmospheric layer of the exoplanet. So that's why people are getting fancy to observe titanium oxide, and also titanium oxide can give us some data about the atmospheric range of the exoplanet, or which kind of species can be found in the range of the, or which kind of gas range in the exoplanet. So there is a news currently going around the internet that the exact hot Jupiter I'm looking at, it rains iron. So we are also looking at this kind of thing, that if there is any connection between that titanium oxide and iron rain in atmosphere of any
Sorry,
hot
did you
Jupiter.
say iron rain?
Yes, iron rain, because it is a hot Jupiter, and as you see, there is like enough amount of heat to liquefy and evaporate the ions in the atmosphere, and it rains iron in the night side of the planet, as far as I remember. So that's why the WASP 76b planet is very famous nowadays.
That's so cool.
I have a quick question. So, what I'm interested in is like almost, well, I don't know if this is the right term for it, but like the stellar decomposition. So, like, how do you like eliminate, like, I'm gonna put this in air quotes, like the contaminant of like the stellar spectrum, because I can imagine that the like atmospheric like signature is like a lot weaker. So how do you also, like, to build on that question, or did this paper mention, like, how do you kind of parse through like spectra and figure out whether you have an atmospheric detection in it?
So, like what I'm doing, that we have already predicted model of like a species in what we have observed in our solar system using our own Jupiter and our own Earth. So there is some kind of models that predicts a water signature, titanium oxide signature, methane signature, or carbon to oxygen or carbon oxygen monoxide signature. So what we do is we have a model and we just match what the correlation process does, that we just match the both things, and we see if we see the two model and our data matches, the cross correlation will just show the peak in the signature. That's how we just get the idea that there may be some this kind of species, but as there is a thing that when we are doing the literature review, we found a paper that basically explain that the hot Jupiter I'm looking, 76D, they have titanium oxide, but they measured it using low resolution spectroscopy. So, and we are going to do the same thing, but we are doing high resolution spectroscopy. But we are not totally sure that if high resolution is correct or our low resolution is correct, but we are not sure. But what my advisor said, that only one of us may be right, because there is a debate going around that if there is any titanium oxide available or not. But if we found titanium oxide in our examining or our project too, we can definitely say that as we have two different kind of methods and two different kind of methods on the same species, maybe there is a probability that okay, maybe we have a signature for titanium oxide. That's how the thing goes. Like we have different methods, we have different people working on different kind of cross correlation methods, and if our data matches, the end result matches, we can like directly say that yes, there is a species like that for oxygen or titanium oxide or water or something like that. And maybe you tried to mention that yes, we can see the atmosphere, we can predict what kind of atmosphere is there. Is there any opportunity, or is there any case that we can also measure the surface or the composition of the planet itself? It's an interesting question, I guess, but I don't know exactly how to measure this kind of thing, how to explain or how to measure the exact surface quantity or surface composition of a planet. But we can predict it using our own Jupiter or our own solar system planet. I don't know the details in that for that. I hope, Celia, you got your answer. That I basically I'm Jon Snow. I don't know nothing. I don't
Yeah, no, that was really helpful. Thank you. I just think it's like so like interesting that we can do this, because when you like really think of it, it seems like something so impossible. Like the first time I heard about exoplanet atmospheres being detected was maybe like 2 years ago, when a class, like I was taking a data science class and we were reviewing the decadal survey, like the United States decadal survey, and there was one about detecting like nitrogen in the atmosphere of like an exoplanet, and I was like, wait, that is just really wild. So yeah.
So have you ever wondered about like the atmospheres of the movies they showed, like in like Avengers or any kind of movie like that, or Avatar? Have you ever wondered, oh, these guys are breathing like extrasolar planet atmosphere? How this supposed to work? But in Avatar, they showed us that it's not breathable because there is a certain amount of argon or neon, which is not uh, healthy for human consumption. So they use some kind of mask in Avatar. But when you see the Avengers Infinity War movie, so they went to another planet named Titan, and they're breathing the air. But for humans, it's don't supposed to not. It doesn't supposed to work like that. Like Tony Stark or other people are humans. They don't supposed. They are not involved into that particular planet, so they are not supposed to breathe the air from that. But they're doing that. So if you think it's scientifically, you get so many questions. I think this kind of fascination and wondering about the things are cool. So that's how I got into that exoplanet thing. I watched Avatar, not the Avatar Last Airbender, Avatar. So any question?
That's fantastic. Just gonna put that out there.
Any questions or any suggestions for me to improve? Sarah?
No, it's a challenging platform to do like online. So yeah. And we can also keep chatting offline in the Slack if anyone has any more questions. Maybe it'd be great to share that was it the WTF paper where the